So in the last lecture we learned that if a matrix has an eigenbasis, that is, there are n linearly independent eigenvectors associated with that matrix, then it can be represented as this product, where D is a diagonal matrix which contains the eigenvalue of matrix A on its main diagonal, and X is a matrix which contains the eigenvectors as its columns. An advantage of this diagonalization is that we can easily compute the power of matrices. For example, the kth power of this matrix is simply equal to X, and the kth power of this diagonal matrix multiplied by X inverse. And finding kth power of a diagonal matrix is quite simple. Simply we take the power of entries on the principal diagonal. So please determine the power of this matrix A power 8. So we need to determine this matrix D, that is the eigenvalues of this matrix A, this determinant equal to 0. From here you write the characteristic polynomial, and once you have characteristic polynomial, which in this case is lambda square minus 3 lambda plus 2 equal to 0, that gives you eigenvalues equal to 1, and second eigenvalue is 2. Corresponding to these eigenvalues, we can easily determine eigenvectors, and eigenvector corresponding to first eigenvalue lambda 1 I is the solution to this system of equations. Eigenvector corresponding to this eigenvalue, that is equal to, similarly corresponding to second eigenvalue, we have this eigenvector, and therefore this matrix X is simply the matrix which with these vectors as its column vectors. Hence this matrix A, that is equal to, so first we also need to determine X inverse. So we have X given by 1, 1 and 3 by 2 and 1. How to find its inverse? You can proceed in different ways. For example, by performing the row operations, or you can also find the inverse of this matrix by the method of determinant, that is, so this X inverse, so this X is not unique because these eigenvectors are not unique. Yes, because there is also inverse of X over here, so it will always be the same. And then this matrix A power 8 is simply equal to X, which in this case is this matrix 1, 1 multiplied by diagonal matrix, and diagonal matrix contains the eigenvalues of this matrix on its diagonal, and the sequence of this eigenvalues should be like this one. If you write the first, this is the eigenvector corresponding to this eigenvalue, so we should write this eigenvalue over here, and 0, 0, and the second eigenvalue is 2, and we want to determine the 8th power, so that is by this expression, 8th power of 1, which is 1, and 8th power of 2 multiplied by X inverse. So this is the 8th power of A. You can simply multiply the matrices, these three matrices, to determine the 8th power of this matrix A, which finally comes out to be equal to, yes please. So the question is, if some eigenvalues have algebraic multiplicity more than 1, then can we diagonalize that matrix? So what is the answer? Depends. If we can find n linearly independent eigenvectors, then we can diagonalize that matrix. Otherwise we cannot. So we have studied situations when we had algebraic multiplicity more than 1, but geometric multiplicity was not equal to algebraic multiplicity. In that case, we will not have n linearly independent eigenvectors for that matrix, so that matrix will not be diagonalizable. So this is the 8th power of this matrix. Here the only difficulty in all this computation is only finding x inverse. That involves some computations. However, if the matrix A, if matrix A is symmetric matrix, then for symmetric matrix, this matrix X is also orthogonal. For symmetric matrix, this is orthogonal. So symmetric matrix A has, if this matrix A is symmetric matrix, then it has an orthonormal basis of eigenvectors. X is orthogonal matrix, that is X transposed is equal to X inverse. So if this matrix A is symmetric, then computation of this thing becomes further easier, because finding X inverse will be easier. X inverse will be simply equal to transpose of X. So to demonstrate it, please diagonalize this matrix. So these vectors, eigenvectors, are not unique. So you will find the eigenvectors which are orthonormal, orthogonal as well as normalized. So this example will demonstrate the concept. This is a symmetric matrix, and you can find the eigenvalues for this matrix. So these are two eigenvalues. Corresponding to these two eigenvalues, we find eigenvectors, and the second eigenvector, this corresponds to lambda equal to 6. Lambda equal to 6, this is an eigenvector, and corresponding to lambda equal to -2, this is the eigenvector. These vectors are orthogonal, and however these are not orthonormal. So what we need to do that is normalize these vectors. So what is normalized vector? So the entries divided by magnitude of that vector. So 1 over square root of 2, 1 over square root of 2. Likewise, this vector normalized is 1 over square root of 2 and -1 over square root of 2. So this matrix X, this matrix will be orthogonal. By orthogonal matrix, we mean that its inverse of this matrix. What is inverse of this matrix? Simply transpose of this matrix is its inverse. So that is, so this X inverse, computation of X inverse becomes more easier, because we have to simply take the transpose of that matrix, and hence you can find, you can diagonalize this matrix. So this matrix A is simply equal to x multiplied by this thing. So if I take 1 over square root of 2 common from this expression, diagonal matrix contains the eigenvalues on the diagonal, so corresponding to this eigenvector will be the diagonal value, or will be the eigenvalue over here. So 6, 0, 0 and minus 2. And again from here we can also take 1 over square root of 2 common. So this square of 2 multiplied by this square of 2 is 1 by 2 multiplied by this matrix, inverse of x. So this matrix has been diagonalized. So the question is why we have normalized these vectors. We have normalized these vectors to make this matrix orthogonal. This matrix will be orthogonal when these vectors are orthonormal. What is orthonormal vector? So here we see that if we do not normalize this vector, so let's call it x1 and this one x2. So these two vectors, this vector and this vector, these are orthogonal. Orthogonal means that x1 transposed into x2, what is that? That is equal to 0. So so that is equal to 0. x1 transposed into x2, that is equal to 0. However, what is x1 transposed into x1? What is that? So 1, 1 multiplied by 1, 1. So 1 plus 1, that is equal to 2. So these vectors, likewise you can find the magnitude, the magnitude of this vector. That is, you can also find x2 transposed into x2. That will, so these two vectors x1 and x2, these are orthogonal, but these are not orthonormal. So to make them orthonormal, we have also normalized these vectors such that computation of this inverse becomes easier. If this matrix is orthogonal, then its inverse can be simply obtained by writing the transpose of that matrix. Yes, definitely. So the question is, these two vectors, these are eigenvectors, right? And these eigenvectors span R2 in this case. So therefore, these are also an eigenbasis. So the question is whether these two vectors which are normalized, all these also eigenvectors and all these also constitute eigenbasis. So answer to both the questions is yes, these are eigenvectors. Any scalar multiple of this vector is also an eigenvector. Likewise, any scalar multiple of this vector is also an eigenvector. So these are eigenbases and this one is also eigenbasis. Eigenvectors are not unique, so any set of eigenvectors which spans Rn, that is called eigenbasis. So again, eigenbasis is also not unique.